Hello. I can be heard but not seen, apparently, because Meet Echo is not letting me turn my video on. How about now? Oh, there we go. Anrw, I have the videos queued up too, but since you're sharing the screen, do you want to play them? I just wanted to check.
I think Meet Echo will help us just to play the videos.
Here
just need to ask them. Yeah. Hi,
can you hear me?
Yeah, we can hear you loud and clear, and we can see you.
Check testing. I see audio waveforms suggesting that I can be heard. Okay, awesome. Great. So welcome everybody. I cannot hear you. Oh, that is why. Hold on a sec. I need to unmute this tab. Hello? Can you hear me?
Hi again. Yes, we can hear you.
Oh,
now.
Perfect. Yeah, I was muting myself, you know, because there's 16,000 Zoom meetings going on at the same time. So,
yeah, no worries.
Welcome everybody to session 5. In this session on DNS and privacy, again, we'd like well, we thank the sponsors, but also let's remind everybody of the logistics and the links here. So there is a Slack channel. If you have, questions and such, that's a good place to put them. I will see them. Anrw, our talented session chair for the last session, will also see them. And that's a good place to do that. The URL here for your convenience, where you can access the program, the papers, and also the videos that you're about to see, are all on the program website. Thanks to Colin Perkins, who's also here. Great, thank you for putting everything up. So you can watch those again if there's something you really liked. And then also, if the papers themselves are also available in the ACM digital library for your viewing pleasure. If for some reason you want to follow up and read the papers, they're all available there. As a reminder, all these sessions are recorded, and the recordings will be available on YouTube after the workshop. So looking forward to an exciting session. Okay, yeah, a couple more points here. The videos that the presentations that we're about to see are pre-recorded. So we'll take questions at the end in a 5-minute slot. And then at the end of each session, we've got a 2-hour slot, but each session runs an hour. So we're going to end each of these sessions with a 15-minute panel for Q&A for all the authors presenting in the session. Our rationale for that was we thought it'd be a little bit more lively than just a presentation or back and forth with a single author. So we organize things thematically. So hopefully we'll have a fun discussion on DNS privacy towards the end of the session. Just some Meet Echo stuff. To ask a question, just enter the queue, the mic and hand logo, and then I will call you out and enable the audio. And if you need more information on how to use Meet Echo, there it is. Next slide. Yep. So here we are, session 5, and our first presentation will be from Austin Hounsel. Austin, I see you're here. Long time no chat, Austin. And not only am I the session chair, I'm also a co-author on this paper. So, so no hard questions, right? No. But Austin, we're going to play the video now, so we can cue that up. So we can ask the Meet Echo folks, wherever they are, to play Encryption Without Centralization. Thanks.
Solo un momento. Hi, my name is Austin Hounsel, and I'm a PhD student at Princeton University. And I'm going to be presenting some work today about distributing DNS queries across recursive resolvers to reduce centralization. This work was done in collaboration with Paul Schmidt, Kevin Barkolta, and Nick Feimster. So essentially, we are presenting the design and prototype implementation of a refactored stub resolver that allows for decentralized encrypted DNS resolution. We then perform a preliminary evaluation of the stub resolver's performance and utilize a real-world data set to evaluate how various query distribution strategies, such as random, round-robin, and hash-based strategies, affect the amount of queries that are seen by recursive resolvers. So as we know, DNS privacy has become a significant concern within the past few years. We know that on-path network observers can infer which websites you're visiting by looking at your plain text DNS queries. This kind of interference can occur within governments or in coffee shop networks, etc. So two protocols have been proposed to encrypt DNS traffic. One is DNS over TLS or DOT, and the other is DNS over HTTPS or DOE. And we're seeing that increasingly DOE is being rolled out by various browser vendors and other software developers. In fact, we're seeing that Firefox now uses DOE as the default DNS protocol for US users, which, you know, encryption is a great thing. It's great that encrypted DNS is being increasingly deployed. However, with it, some users are growing concerned about ways in which the DNS may be centralized into a handful of large operators. And so we stand to ask, well, is there a way we can get encrypted DNS resolution while distributing our queries across multiple operators instead of centralizing into a small set? So first, we want to ask, well, is decentralization even worth doing in the first place? What might be the theoretical reasons why you may or may not want to distribute your queries across multiple resolvers? However, we're not going to be answering that in this talk. Instead, we're focusing on, well, is it even technically possible or feasible to distribute queries across resolvers? And what forms could this decentralization take? So the architecture we have in mind goes something like this. In step one, the stub resolver discovers various upstream resolvers that support DOE, along with the characteristics of these resolvers, such as geographic location. The user can specify these requirements, such as within a configuration file, and then the stub resolver then selects of this pool a set of DOE resolvers that match the characteristics the user desires. The stub resolver then, as it receives queries, distributes them across multiple resolvers according to some user-specified strategy, such as a random model or a round-robin model. To prototype this, we forked DNSCrypt proxy, which supports DOE and DNSCrypt, and we added support for the hash and round-robin model, and we also evaluated some existing code that was within the proxy for random query distribution. We evaluated the performance of this. We note that the proxy can not only run on host devices, but also on routers, and so maybe we will support distributing queries for a given strategy for an entire local network. So this is just a quick example of what it looks like to use a hash-based model that we implemented. So for example, if the stub resolver sends out a query for example.com, or receives it rather, it may then forward it to Cloudflare's upstream DOE resolver based on hashing of the second level domain name. For images.example.com, it would also get hashed to Cloudflare's resolver because it shares the same second level domain name with example.com. Similarly, New York Times might get mapped to Google. And then if the client queries it again, it gets mapped to Google once again, same domain name. And then the Washington Post goes to Quad9. So we're seeing that the DNS queries are no longer just going to a single DOE resolver, but being distributed across multiple of them. Similarly, the round-robin model behaves as you might expect. First query goes to the first resolver, second query goes to the second resolver, third to the third, and so on and so forth. And lastly, in the random model, also might behave as you might expect. The queries go to various resolvers without a particular order. So we wanted to evaluate these strategies and see what's the effect of a stub resolver that implements these strategies on both page load times, CDN localization, and the percentage of unique domain names that are seen by various resolvers from each client. So we're going to be answering these questions in turn. So first we turn to CDN localization, right? And what we're particularly concerned about here is what is the effect of using various recursive resolvers on how far away the CDN content is that you resolve, right? So if we look at this figure, which is a CDF of TCP and TLS setup times for CDN content, we can read the legend in this way. If you look at the Cloudflare-Google line, what we're seeing there is that this is the CDF of TCP and TLS setup times when you use Cloudflare's DOE resolver to resolve Google CDN content. And essentially what we're seeing here is that there really isn't too much of a difference that's being made in terms of using one particular resolver to host, to resolve CDN content. In other words, you could use Cloudflare's resolver and get Google content just fine, just as you can use Google's resolver to get Cloudflare content just fine. Similarly, in terms of page load times, we're seeing that no single strategy seems to have the best or worst effect on performance for page load times. So these are measurements that were taken from 4 Amazon EC2 vantage points in which we perform page loads using a instrumented instance of Firefox with Selenium, a headless browser. And we perform measurements with 3 different query distribution strategies, right? And so what we're seeing is that no single resolver, once again, or rather no single model, seems to perform the best or the worst. Across different vantage points, we're seeing slightly different effects on page load times, but everything looks about roughly the same. And then when you turn to a comparison of using a single resolver for all your queries, we're seeing a similar story where each resolver seems to perform somewhat similarly in terms of its effect on page load times, whereas in certain vantage points, you're seeing maybe a slightly higher effect than in other ones, right? So for example, if you look at Oregon, you might see that there's a much more pronounced difference in page load times with certain resolvers. And then lastly, we look at the effect of how many unique domain names are seen by DNS resolvers whenever you use query distribution strategies, right? So we utilized a real-world data set from Allman et al. Of 100 homes in Cleveland, Ohio that were connected to a fiber-to-the-home network. We utilized this traffic to perform our query distribution strategies after the fact, so to say, to kind of simulate what would this traffic look like that is sent to various resolvers if we were to use our query distribution strategies in the first place. And so what we're seeing here, if you look at figure A with the hash distribution strategy, is that if you use 2 resolvers, 4 resolvers, or 6 resolvers, there's a kind of flat line in terms of how many unique domain names from a given client's queries are seen by various resolvers on average, right? And this is fairly intuitive to understand because if you think about it, in a hash-based model, the same queries for the same domain name should always go to the same resolvers. It shouldn't be the case that 2 resolvers ever receive a query for the same domain name. Whereas if you look at the round-robin model, within the first couple of weeks, we see that each resolver starts to gain access to more and more unique domain names from a given client. And this makes sense because the round-robin model doesn't have a fixed mapping between domain names and resolvers. Nonetheless, it is interesting to see that the percentage of unique domain names does kind of taper out over time. And we think this is because in the traffic data, there's a lot of queries for popular domain names and fewer queries for less popular domain names. So in summary, we presented the design and prototype implementation of a refactored stub resolver architecture that allows for decentralized encrypted DNS resolution. We performed a preliminary evaluation of the stub resolver's performance and utilized a real-world data set to evaluate how do different query distribution strategies affect how many queries are seen by recursive resolvers, right? Our goal of this work is not to suggest that we necessarily should be using query distribution strategies everywhere, or that we should be using these exact strategies or in a particular manner, but rather to explore what is the feasibility of a distributed DNS architecture in which we don't just send encrypted DNS queries to a single resolver or maybe a small set of resolvers, but rather distribute them across a larger set of resolvers. And we're planning on doing some follow-up work to see what does your performance look like if you use a lot of resolvers that are in different geographic locations, and how does this affect a client's privacy in a formal way rather than the preliminary evaluation that we've done? Is there a way that we can formalize the privacy costs and benefits of using different query distribution strategies? So I want to thank you all for listening to this talk, and you are more than welcome to contact me at the email above, and I'd be happy to answer any questions. So I want to thank my collaborators. I want to thank the audience for listening, and yeah, thank you very much.
Thanks, Austin. Great talk.
Can you hear me?
Yeah. Hey, Austin.
Hey.
I think, let's see. I don't know if we have your video on, but I see a queue of 2 questions. So let me figure out.
Turn my video on.
Yeah, I've got a question from Jim. Oh, oopsie. Removed from queue. Jim, how Do I enable Jim's?
It looks like we don't have any guests in this
That should be
demo
enough.
session.
Jim is there. Jim, just ask the question.
Yeah, can you hear me?
Yeah.
Yes, we can hear you.
Excellent, excellent talk, Austin. I was a little bit confused by you were saying that when you're querying these resolving servers, that things are working out fine between, say, Google and Cloudflare and all the rest of it. If I understand correctly, the Cloudflare resolver service doesn't implement ECN, client subnet. So the information it's returning may not necessarily be an optimal IP address, say for something that's hosted on another network, or because of the routing information. So I wonder if you've made any attempts to try and adjust that or take account of that in your measurement data, or is that something to look at for the future?
So thanks for the question. So I would say that we've been thinking more and more about CDN localization as we start thinking about doing collaborations with some folks in Cape Town. And we're planning on doing some measurements across Africa to see, you know, okay, if we can take these resolvers in North America and these clients in North America and extend our results to other countries, would we see similar effects in CDN localization? And what we're quickly starting to realize is that we're going to have to think a bit harder about the evaluation we've done so far with regards to CDN localization. It's not quite as formal or as sophisticated as it could be, and we've definitely been thinking about questions related to EDNS for future work. But that's not something we explored for this paper.
Let's see. We've got a question from DKG. If I can.
Hi there.
There we
This
go.
is Daniel Kahn.
Hey, you can speak. Hey.
Thanks for doing this work. Austin, I really appreciate that you're trying to figure out how to formalize this. And I wonder whether you have any thoughts about the privacy implications of the two schemes that you have beyond information learned from the DNS resolver. So for example, in the hash-based scheme, it looks to me like each client is basically, I'm assuming that each client doesn't pick the same hash-based scheme. They're probably keyed by some individual selected hash. And I wondered,
Right.
That looks a lot like a super cookie to me. It seems like somebody on the local network could force you to do, or encourage your browser to do a number of lookups, observe which lookups you do to which servers, record that, and then have a fingerprint of like who your device is that
Right.
they would find over time. So when you're formalizing the privacy evaluations, are there metrics like that that you plan to include? Like, how are you thinking about this?
So, gonna be honest, that is a scenario that I had not thought about in my head. The potential for using that kind of hashing strategy as a super cookie, and I think that's very interesting to think about. You know, another kind of question that comes to our mind is, you know, so it may seem beneficial in the hashing scheme to, you know, use the second level domain of a domain name as a way to ensure that all, you know, domains that are related to each other should go to the same resolver. But then there's a further question, like, does it matter whether certain domain names at all go to certain resolvers, in the sense that, you know, maybe there are certain sensitive domain names that you wouldn't want to go to a certain operator's resolver, right? Maybe that would reveal more information about you than you would like. So there's also a question of, you know, is there a way that the client could provide some kind of a preference about resolvers that it might wish to use to avoid certain ISPs, to avoid certain geographic locations? And, you know, there's a lot of considerations beyond just, you know, okay, how many resolvers do you use, or which resolvers, but also at what locations, across which ISPs, you know, if they're ISP operator resolvers, maybe you wish to use them or not. So those are also considerations we're thinking about. But I guess to answer your question directly, I had not thought about that scenario that you brought up, and that's definitely something to write down as we start thinking about formalizing this for future work. So I really appreciate that question.
Great, and I think we have we have at least one more person in the queue. Sarah has a question. Sarah Dickinson.
Hi, can you hear me? So this is slightly orthogonal to the idea of privacy, but it feeds in again to the idea of user experience. When you're talking about collecting sets of recursive resolvers, it might be worth just including in that the characteristics of the resolvers in terms of, for example, filtering or DNSSEC, because otherwise you'll get different results from different resolvers potentially, which could lead to very strange user experience in intermittent behavior.
Right.
So just another thing to add into your selection criteria.
Yeah, absolutely. And I should say as well that we've already begun doing some work to kind of explore whether we can do some kind of a user study to explore, okay, do users have any understanding of what it might mean to distribute queries across multiple resolvers? What is DNS privacy to users, even technical users, right? And that's very much going to inform among a wide variety of questions and preferences, like what would the default settings of such a system be? It's something that, you know, we frankly, like, we're kind of hesitant to provide any kind of an answer for at first. Like, you know, we don't, maybe there shouldn't be a default strategy, but, you know, in terms of user experience, users probably do need some kind of default, or they're not going to set it themselves. And it's not immediately clear to us whether one strategy is better than another, whether or not, you know, some users may want filtering resolvers or not, in terms of, like, you know, if I'm a parent in a household, you know, would I want a filtering resolver versus if I'm somebody that is not a parent, maybe I don't want a filtering resolver at all. And how do you make these kind of default decisions for users without trying to make them get bogged down too much in the details? And so that's definitely a consideration that comes to mind, especially as we look at various lists of DOE resolvers out there. Like, I think DNSCrypt has one on their GitHub page, and I think in one of the columns they indicate whether or not it's a filtering resolver or not. And that was something that came to our mind, is like, well, yeah, like, you know, if we're going to be doing measurements across many resolvers, you know, we got to be sure that we're going to get the answers that we're going to expect just from a scientific perspective. So that's definitely a consideration we've thought about.
Siobhan, we have one more question in the queue. I know we're a little over time for the first talk, but let's take a rest. Siobhan,
can you hear me? Sorry, can you hear me?
Yes, we can.
Oh, cool. Thanks. Yeah, this is not a fully thought out idea, but to address what PKG brought up earlier about fingerprinting concern, would it help at all if there was if globally it was the same domain name to resolver mapping, and everyone, all clients would use the same, you know, second level domain mapping to resolver? Like, this is not ideal, but it would at least, I mean, you would still be able to find out that, you know, for certain domain name, like everyone's queries are on this resolver, like an attacker would be able to do that. But this would, I mean, this would still be better than the status quo, perhaps?
Yeah, that might be better. I mean, something to consider too is whether even the hash-based strategy is the best we can do in terms of privacy, right? Like, even if we all agreed that we should use the same hashing scheme for all clients, maybe we can do better in terms of privacy than hashing domain names. It's something that we're still thinking a lot about, because we're not entirely convinced that that's the best we can do. And yet it's something we're still actively thinking about.
Thanks, Austin. Great questions. I see there's one more question, but I think we definitely should probably get on. So, Hisham, if you could hold your thoughts until the panel, that would be appreciated. Hang on to that thought, because we're definitely up against time here. So, let's, to the Meet Echo folks, maybe we can queue up our second talk, which is institutional privacy risks and sharing DNS data. So, looking forward to that one. Thanks.
Hi, everyone. My name is Basi, and I'll present our work on institutional privacy risks and sharing DNS data. This is a joint work with my PhD advisors, Professor Alexandra Korolova and Professor John Heidemann. Almost all online activities, such as accessing a website or sending an email, start with a DNS query. Therefore, DNS queries can say a lot about end users' online activities, and this privacy risk has been well understood and studied in the past. In our work, we introduce a new aspect of DNS privacy, which we call institutional privacy, which is concerned with the behavior of an institution's traffic as a whole. In contrast to individual privacy, this has not been closely studied before, but it's important to look at because institutions' internal activities, such as sending or receiving an email, can leave a digital trail in the DNS ecosystem. Based on this motivation, our contributions in this work are first to define institutional privacy as a new privacy risk in DNS. And within this threat model that we define, we give a methodology for finding institutional privacy leaks. And then we apply this methodology to a real world data that's anonymized and show the privacy risks and also demonstrate that the anonymization method that's used is not sufficient to prevent institutional leaks. To start off with how we define institutional privacy, we broadly define it as confidentiality of digital footprints of an institution's internal activities. Examples of specific activities that may leak information through DNS include, for example, two institutions sending or receiving an email between each other, which may reveal a relationship between them that's not known publicly, or another activities, an employee of a company accessing a privacy sensitive or website that's considered embarrassing from the company's perspective, such as like an illegal or an adult website, and accessing such websites while on the company's network. For our threat model, we consider an adversary that's the authoritative server and has either access to the server logs or the traffic between the recursive and the authoritative server. And the goal of the adversary is to associate the source IP and the domain name in the query to the corresponding institution. The adversary targets an institution that meets two kind of conditions. The first one is the institution must run its own recursive resolver. This would let the adversary use the resolver's IP address to uniquely identify the DNS traffic of the institution. And the second condition is the institution must route traffic from its own autonomous system. And this would let the adversary map the resolver's IP address to the corresponding autonomous system that's owned by the institution. Many institutions' adversaries fit our threat model. In our study, we studied queries from six institutions that meet the conditions that I just listed and also represent a diverse set of sectors, such as large S&P 500 companies, government institutions, University of Southern California schools, and so on. And when we pick these companies, we exclude institutions that have apparent deniability, such as ISPs or hosting service providers, because queries from these companies might be coming from their customers and not from their employees. And examples of potential real-world adversaries in our threat model include DNS service providers and also researchers that have access to data that's shared by the service providers for research purposes, and also government-level actors that have the means to eavesdrop on DNS traffic. In this talk for our methodology, I focus on how we associate queries with an institution and how we find queries related to email, but there is more in the paper. As I mentioned earlier, the goal of the adversary is to associate the source IP and the domain name with an institution. So for the source IP, we use public IP to AS number mapping data to map the source IP to the institution that owns the AS. And this works even if partial preserving anonymization method is used. And second, for the domain name, we use a public whois data to map the domain name to the institution that owns the domain. Here we assume the domain is in full and not that QNAME minimization is not being used. Once we identify queries related to an institution, we filter out, we'll filter and find queries that are related to email exchange. The first one is MX queries, which are made by mail servers before sending an email. And in this case, the source IP of the query identifies the sender of the email, and the domain name in the query identifies the intended recipient. And the second type of query we look at is DNSBL queries, which are made by anti-spam services upon receiving an email. In this case, the source IP identifies the recipient of the email, and the IP address that's embedded within the domain name identifies the sender of the email. We apply this methodology to 1 week of beroot data, and we also reproduce our results on a second week. This data set is anonymized using a prefix preserving method. The bottom 8 bits are anonymized. And we run this experiment with IRB approval and with the permission of the data owners. And the research questions that we looked at are first, how common are sensitive email related queries? And then within these queries, are we able to find specific relationships between institutions that's not otherwise publicly known? In the paper, we also look at how common are queries to sensitive sites, which I won't cover in this talk. So first, we looked at how common are MX and DNSBL queries in the data set that we looked at. This plot shows the x-axis is the 7 days of data that we looked at, and the y-axis is the number of queries in millions. And we can see that several millions of DNSBL and MX queries are made each day, which can be a significant source of leakage of email-related traffic. And within this millions of queries, we can go further and ask, are we able to narrow down and look for specific relationships between institutions? And in this slide, the plot on the left shows a breakdown of those MX queries by the different sectors of companies that we studied. And the plot on the right narrows down even further and looks at queries made to specific institutions such as Palantir. And we mentioned some examples of specific relationships that we find. For example, U.S. Department of Justice IP address requesting MX record of Palantir.com, which is in line with the known fact that Palantir works with government agencies. And another example is a school board in Jefferson Parish requesting MS record of ICE, which is also in line with the known fact that this parish is known to work with ICE in their deportation efforts. We show these examples just based on 1 week of data, but we expect a more dedicated adversary that can look at a longer duration of traffic to find even more institutional privacy violations. So based on this result, our recommendations are for institutions to deploy query name minimization wherever possible. So we recommend an even faster adoption of this mechanism. Another option is to use a mechanism called local root, which caches the root zone locally so that the recursive resolver does not have to make queries to the root server. And for service providers, our recommendations are, first, we have shown that host-only anonymization is not sufficient for protecting institutional privacy. So we recommend service providers to put legal constraints when sharing DNS data, and for the case of wider sharing where that's not possible, that they look into more rigorous privacy preserving data sharing approaches. In this work, we have shown that DNS queries may leak significant institutional information that's otherwise not publicly known. Therefore, we recommend institutions deploy queue name minimization wherever possible, and that service providers evaluate institutional privacy risks when sharing DNS data for research purposes. With that, I conclude my talk. Thank you for listening. Our paper and data can be found at the link shown on this slide. Thank you.
Thanks so much. I waiting to see. Oh, good. We've got Hisham in the question queue. Hisham, I'll remove you, and hopefully you can speak up.
About using differential privacy to ensure that the data of the institution is not going to be revealed to the intruder?
I think maybe the first part of the question was cut off a little
Yeah.
bit. Maybe
Have you thought about using differential privacy to protect the privacy of the institution so that the intruder doesn't know who is which institution this query is coming from? I'm talking about the differential privacy.
Basi, can you hear the question? Questions about like, have you considered the use of differential privacy to essentially make it more practical or possible to share some of this data across institutions? I think
Yeah,
that was
exactly. That's the question, exactly.
Yeah.
Hello?
Maybe we're having a little bit of AV problems. Basi, can you hear us? Seems okay. Maybe
Okay, I think I can
here
hear
we
you
go.
now.
Hi, Basi. Yeah.
Sorry.
Heard the question, right?
Sorry, I think I missed the question.
Okay, let me restate it. Can you hear me now?
Yes.
The question was from Hisham was, have you considered the use of differential privacy to make it more feasible, practical to have institutions or organizations share this DNS data that you're talking about in your talk?
That's a good question. It's also one of the things that we recommend in the paper, but we haven't actually done the work to see how that would be applied in the context of sharing DNS data. But certainly that's a possibility.
Hey, thanks, Hisham, for the good question. Yeah. Seeing nothing else in the queue, and given that we're like a little bit behind time, I think I'll ask Meet Echo to queue up the third video. And that'll leave us hopefully time for Q&A on that talk, as well as a little bit of group panel discussion at the end, where I'll ask all of our speakers to join again. So here we go, talk 3.
Hello, everyone. Welcome to our presentation. I am Tianxiang Dai. I'm here to present our work DNS over TCP considered vulnerable. This is work together with Dr. Haya Schumann and Professor Michael Weisner. We are all from German National Research Center for Applied Cybersecurity at Center in Darmstadt, Germany. In this presentation, we will first briefly introduce our motivation about this work, and afterwards we show our evaluation in the internet. Based on the evaluation results, we present a potential exploit. Afterwards, we propose some countermeasures and then conclude our work. Our motivation is based on our previous work on DNS over UDP. So we all know that DNS over UDP is vulnerable to IP fragmentation attacks. So then another question is that, what about DNS over TCP? Is it also vulnerable to IP fragmentation attacks or not? So we searched some related works. We find out that it's well believed that IP fragmentation attacks doesn't work with TCP. For example, there's a draft best common practice. IP fragmentation considered fragile. It says there's alternatives to IP fragmentation, which is using TCP with PNTUD. There's also another best common practice in draft fragmentation avoidance in DNS. It says TCP is considered a resistance against IP fragmentation attacks. Also, in last year's DNS Fragment Day, which is the event for among the DNS operations community, it says TCP normally implements PMTUD and can avoid IP fragmentation of TCP segments. So it is real. Does DNS over TCP really protects against IP fragmentation attacks. To check this, we designed our evaluation in the internet. So we want to trigger fragmentation over TCP on name servers in the internet and then compare with UDP. We designed follow evaluation. So we have our resolver and we find some name servers in the internet. We first establish a TCP connection to the name server and then send the DNS query over the TCP connection. After get the response, we send ICMP packet too big to indicating our MTU on the road is too small, and we wait for the DNS response retransmission. As a comparison, we do similar evaluation over UDP, but considering UDP is the connectionless protocol, so it's a little bit different. We first send the DNS request and then get the response. Afterwards, we send ICMP packet too big. Instead of waiting for the retransmission, since there's no UDP doesn't do transmission, so we send another DNS request the same as before and wait for the second DNS response and check if fragmented or not. Then what's the result? We tested against Alexa top 100,000 domains. In the end, we get about 500 domains fragmented over TCP. As a comparison, there are over 9,000 domains fragmented over UDP, but this is not surprising. We all know UDP is vulnerable to IP fragmentation attacks. When we dig into more details about the fragmented domains over TCP, we find out that the majority of them are only vulnerable to TCP. There's about 20% vulnerable to both and 80% vulnerable only to TCP. When we check among those domains only vulnerable to fragmentation over TCP, we find out that there are even 76 domains which has TCP bit when we test TCP bit set when we test it over UDP. So what does that mean? TCP bit means truncated. It is set when the packet is the DNS payload is too big for the UDP, or when the server is rate limited. In any case, it means the name server has a preference over TCP. So it's the name server try to use TCP instead of UDP. So that means there's just these 76 domains. They try to use TCP, which the name server thought is better, but actually it's vulnerable to IP fragmentation attacks, which make it worse. So we also find out that TCP tends to get smaller fragments than UDP. We find that there are about 40% domains which fragments over TCP. They have fragments smaller than 290, while over UDP, there are about over 90% domains has fragments over 540. So what does this mean? Smaller fragments means more payloads are in the second fragment or other fragments. So that means more payloads are injectable. So this is resulting in stronger exploits, which makes things worse. Based on our previous evaluation, we proposed a potential exploit. So as we presented here, this is the example of a fragmented DNS packet over TCP. So the packet above is the first fragment, the packet in the bottom is the second fragment. So we can inject a malicious payload into DNS via IP fragmentation over TCP. So as we know, so the original DNS cache poisoning is using flooding to bypass the DNS challenge, which is the DNS the DNS transaction ID. It's the 16-bit. It can be easily flooded. So to secure it, so we further introduce some challenges in UDP. Also, in UDP source port, so here in TCP2. So the TCP challenge here, the TCP source port. Here, since here we show the packet from the name server to the resolver, so it's the destination port. And also the TCP sequence number and acknowledge number. Both of them are 32 bits, so it's believed to really hard to spoof. But as we can see, both of these challenges, the TCP challenge and the DNS challenge, they are in the first fragment. So that means if we can trigger fragmentation, we don't need to take care of them. They're in the first fragment. We only need to spoof the second fragment. But when we try to spoof the second fragment, we only need to take care of the IP challenge, which is the IP ID. There are many works about there are many works using make use of IP IDs. We did I wouldn't dig into details here, but we did a quick check. We found out that there are even 2,000 domains still using globally sequential IP IDs for TCP. That means they use the global counter for all the TCP connections. So that means the attacker can just using a second machine to probe the IP IDs and do a just simple linear regression, and then he can easily guess the IP ID, which makes the exploit really workable. So what are the countermeasures? We propose the countermeasures in different layers. For example, for IP, the easy dirty way is just to filter the fragments, or just filter the small fragments like Google do. Google filter all the small fragments smaller than 500, so which make it less vulnerable. But sometimes to filter the fragment will make the network down or doesn't work well. So another way is just to randomize the IP IDs to make it hard to spoof. But still, sometimes it's still vulnerable to some side channel attacks like before. Another way is to disable PMTUD in TCP layer. So their research works find out that PMTUD is not really useful. So we can just disable it, and thus we can just filter SMA packet too big. Another way to countermeasure these attacks is to enable DNSSEC, because DNSSEC is like final solution to all DNS cache poison attacks. But we just need to make sure that DNSSEC is configured properly. There are a few other works about DNS misconfigurations, which make it even vulnerable when DNSSEC is enabled. So make sure. Then our conclusions. We find out that DNS over TCP is still vulnerable to IP fragmentation attacks, and we also doubt that if it's really good to recommend using TCP to avoid fragmentation. That's it. Thank you so much.
Thanks. Thanks so much, Tan-Ting. Do we have questions? I think, yeah, I see Chen Chang online here to take questions. If we have any questions for the speaker, now's a good time to hop in the queue. Thanks for joining us, by the way. I'm sure it looks like it's a very late hour for you.
Yeah.
I see Mark Andrews in the queue. Mark, do you want to have a question? You want to ask a question? Oh, no. Mark, you're up. Oh, I probably have to remove from queue. Let's do it.
DNS cookies as a client using DNS cookies to see whether they were actually infectable. And the second question is, have you looked at the proposed well-known TSIG, a well-known TSIG as a protection mechanisms? It's a draft from 2019 about that in my name as well.
Sorry, I didn't get the second question clearly.
There's a using a well-known TSIG shared secret is one possible countermeasure. In other words, using TSIG for every DNS transaction, using a well-known shared secret is also a countermeasure which is theoretically doable at the DNS server level, at the DNS level. And the other question was, did you actually try do an evaluation against a client server pair which support DNS cookie to see how that went in terms of trying to do a injection with that active?
For the first question about DNS cookie, so we didn't check that, but DNS cookie is used to protect against the DNS cache poisoning. So that works if only concerning DNS cache poisoning. But another issue is about the IP fragmentation attack. It allows general denial of service. For example, even if you can't inject something in the payload, you can still just send some useless second fragment just to disable the DNS response to cause denial of service. Another question about the shared secret. I don't really understand this.
I see a question from Puneet here, or Puneet's in queue. Let me take Puneet out of queue. Puneet, you're up. We cannot hear you. Oh, Puneet, you there?
Yeah. Can you hear me now?
Okay, you're up.
Yep.
Yeah. Hi, thanks for doing this research. It's interesting to see that TCP is also vulnerable. So one thing in the mitigations, I think you should mention, especially now that the IETF is talking about doing DNS over TLS to authoritors. I think looking to the future, that is the long-term solution to transport level cache poisoning risks. Of course, there's still a lot of work to do, but it should be mentioned here.
Yeah, that too. But the transport layer protections only works if it's widely deployed everywhere. So, for example, the DNS over HTTPS before mentioned, it only protects against from the client to the resolver, but still doesn't protect from the resolver to the name server. So if you really want to using the transport layer protection protocols, it must be deployed everywhere. So that's why we didn't include it in the countermeasure part. But that's true. That's still a countermeasure. Thanks.
Sure. Thank you.
Nick, we cannot hear you. You're muted. Sorry.
Sorry about that. We got about 6 minutes to go. I see Peter in queue, but I think let's take Peter's question. It's for Chunsheng. But let me invite our previous two speakers back on stage, if you will, so that we can have a more general discussion about these three papers. Let's see, Peter, you're up.
Hello, I believe you said in the chat that when you cause a TCP server to fragment, that they stop setting the DF bit, right?
Yeah.
So would you suggest as a mitigation that resolvers do not accept packets, TCP packets, that do not have the DF bit set?
Yes, that would be a mitigation. Yeah, it's like quick dirty mitigation.
Okay, thank you.
It's only for TCP packet, for DNS over TCP, or only for all the TCP packets?
Yes, although there's a draft in IETF right now that suggests that UDP senders should also set DF. But
Yeah.
that's a different
But
topic.
that will be tricky since some routers on the road will still fragment UDP packet. But for TCP,
Yeah,
since there's the PMDD, it will using segment MS field to make the packet smaller. So it may work
exactly.
with TCP. For UDP,
Yeah,
maybe not. Yeah.
They should resegment and not fragment. I agree.
Yeah,
Thank
that
you.
too. Yeah, you're welcome. So Nick, you're muted.
Doing that. Hisham, let's, I see you're back in queue. So Hisham, welcome back.
Yes, thank you. This is my question to the first speaker about using different ways of distributing queries using sub-resolver. I was thinking if it happens using either round robin or random or whatever, or hashing, you may end up sending many queries to one DNS resolver, and if it gets very busy, it might not be even, you might bring it to grinding halt, it might not even be able to respond to anything. So maybe another scheme is to measure the load on a given resolver before you send the query to it. And if it is very loaded, maybe you can consider sending it to somebody else.
Yeah, that seems reasonable. I'm not exactly sure what metric we would use to measure load, but the idea seems correct. I mean, something else that we experienced actually as we were testing the software is that from a UX perspective, in general with these strategies, there may be some scenarios where if a resolver goes down, a user may be able to use certain websites, but not others. I'm not sure whose microphone it is, but there's some feedback.
Let me stop it.
Right. So you can imagine, as I think you were suggesting, that if a resolver goes down, you know, that may be a problem for users because they may be able to access some websites, but not others. And from a UX perspective, that might be hard to understand. So certainly if there's some way we can test out load or the reliability of resolvers, that would be great. And I agree with that. It'd be good to integrate that into the strategies.
Yeah, and maybe one way to measure how busy it is by looking at the CPU utilization. You can look at how many queries you have sent so far. Maybe if you send many.
I think your microphone cut off for me for a second. I'm sorry.
Yeah, so there are different ways to measure how busy a given resolver is by, for example, measuring the CPU utilization. You can also say, you can count the number of queries you send to a given resolver, and if there are so many of them that has been sent to it, you can guess it is being very busy and has more loads than others, things like that.
Mm-hmm. Yeah,
that's helpful. Yeah, we did something similar for load balancing in when you have many servers and you would like to load balance the traffic to them. We have ways to make sure you distribute the traffic fairly in such a manner to optimize the performance of the whole system.
Right, and that would seem particularly relevant for the random model if that was something we wanted to use, right? Because you wouldn't want to accidentally use a resolver for many different queries that is under high load, as you suggested.
Yes, yeah, it can fit the random model, you're right. Thank you.
Thanks a lot for your question, Hisham. Well, there's certainly a lot of interest. I don't see too many other questions in the queue. Let me sort of since we have a panel here, let me sort of pose one question. I think it kind of maybe relates to the first two talks a little bit more, but even in the case of Austin, your proposed solution, there's still a proxy that gets to see some of the traffic, right, before it's still encrypted. And so you're kind of moving encryption from the browser into, a different place in the network. What do y'all think about like the implications of that for visibility on the privacy side and maybe on the security side as well, right? So it's just different entities who may get to see that. Maybe it's your ISP instead of the browser vendor, or maybe it's nobody if you're the one operating the proxy, behind the CPE. So there's a bunch of different ways that could go. But that affects privacy. It also affects the sharing discussion, I think, from the second talk. What are people's thoughts on that?
I can go, but if somebody else's thoughts, I don't want to take up too much time. One thing that you and I have talked about, Nick, is particularly related to, if you're an enterprise, you want to be able to, there might be some legitimate reasons why you might want to see the queries that are being sent on the network. And if you're moving, this is just, I guess, true of just using encrypted DNS in general, but the more it's deployed, they may have less visibility into that. And so one thing that you might want to factor in for a query distribution strategy is, if there are certain domain names that are supposed to go to a split horizon resolver, then you might need to integrate that into your strategy somehow, whether it's in some kind of a preference box. You might imagine in the application that runs the resolver, you might be able to indicate like, force these domain names to go to these resolvers, and the user might be able to specify that. And so then from a visibility perspective, the enterprise might be able to run their own encrypted resolver and still be able to see the queries that they need to see in a certain sense, right? Like they may still wish to have access to all queries in order to look for command and control, et cetera. But still, at least in one particular use case, you might imagine being able to say, for these particular domain names, ensure that they go to this enterprise, split horizon resolver. That's one thing you might want to integrate in terms of visibility.
Basi, do you have any thoughts? Like, let's suppose Austin's proposal were implemented. Well, it is implemented. Let's say that you had choice of where to deploy that kind of stub resolver functionality. Like you could move the DOE encryption point to, within the home network for all devices. You could move it to the CPE. You could actually proxy somewhere outside the home. You could, there's a bunch of different places where that could be deployed. Do you have thoughts on that and how that would sort of affect, what you're trying to achieve with the DNS sharing? Oh, and I see we're over time, so I'll respect that in a minute.
We haven't talked more about from the encryption perspective, but just in general from like when we're like thinking about solutions about like some of the threats we're talking about in the paper, like for example, one potential solution might be instead of directly querying root DNS servers, forwarding the traffic to another public recursive resolver that uses encryption. And what we run into is that some of the solutions only shift the threat model and don't actually solve it, because now the traffic becomes visible to the operators of the resolver, even though the traffic is encrypted. So the data still leaks. The data stored in the server still leaks the information. So any solution that we consider needs to take these factors into account as well.
Hey, thanks, Basi. And I think thanks to all our speakers, and also thanks to those of you in attendance who asked such great questions. This was a lively session, and hopefully at the next ANRW, we'll see more papers on this topic. I can see that these are really nice ideas with hopefully a lot of potential for future work, as the questions brought up. So outstanding job, everybody. Really enjoyed it, and I think it is now my turn to turn things over to Anrw, who is chairing our last session on applications and specifications. So I think at this point I'll still be in the Meet Echo, but I won't take the mic. So I will also take this opportunity to bid our audience farewell, and also since I do have the mic here, I'll say thank you once again to Anrw, who's our great session chair for the last session, who was just an absolute pleasure to work with on this workshop together. I hope we get to collaborate again on things like this, and hopefully on other topics as well. And I think I'm probably not alone in saying, Colin, we could not have done this without you. There's like way too many moving parts between the IETF and the ACM. So we really appreciate like your experience on that. So I'll turn it over to Anrw for the last session and the last words as well.
Thank you so much, Nick. And likewise, has been a pleasure working together. And we do have a closing piece at the end, so hold on for 2 more talks. So I'm trying to show you what we have in store now, but apparently I'm not able to. Sorry about this. Yeah, apparently I'm not able to, but hopefully everybody has seen the program for the last session. We have 2 very interesting talks. One about how we can interpret better RFCs, and how Bharat is here, and he's going to do the 5 minutes Q&A after the pre-recorded talk. And then we're going to hear from Ali, and he's going to discuss, well, it's a call for action, essentially, about how we can write better specifications for particular applications. So I'm just going to ask Meet Echo to load the video. And meanwhile, I'm just going to remind everyone, we're going to just run the session just the way that we have seen before. So queue up for questions. And again, it's a pre-recorded video, so questions at the end. And we're going to have a panel at the end of this session with questions for both speakers. So that's it for me, and thank you so much.
Hi there. I'd like to tell you about tools for disambiguating RFCs. This is work led by our grad student, Jane Yen, along with Ramesh Govindan and myself, Bharat Raghavan at USC. In nearly every talk I give, I somehow keep coming back to September 1981. This is when the foundational protocols of the internet that are still in use today were defined, and they were written in English and manifested in the world, in Clarke's phrase, through rough consensus and running code. So what I want to ask is, what makes protocols special? Since then, we have grappled with something fundamental about network protocols. They're specified in English, implemented in code through interpretation of that English prose, coded typically in a relatively low-level language, but having a fundamental intent to interoperate with other implementations. Those other implementations went through the same process, interpretation by a person who scrutinized that English text or not, and wrote an implementation that reflected their best guess as to the intent of the spec author. And yet these implementations were written separate in time and space from one another and from the specification, something that rarely takes place in other domains of software development. And from that, we want to achieve all these different properties. We've struggled for a long time to achieve all of them. Properties such as security and interoperability, flexibility, scalability, correctness, and extensibility. And while this is sometimes due to the design and specification process, it's often because of implementations, with issues being discovered incrementally over time. And those implementations get improved, the specifications get improved, and then around we go again. But it's not clear that this is fundamental. And so what we might do is consider different options that we have in protocol specification and implementation. How easy are they to specify, and how easy are they to implement? And not just implement badly, but with all of the properties that we seek. The place we began in our work is the place that we've been some time, that the specification is written in English, and the human and a person somewhere, a human must read the spec, interpret it correctly, and then implement it correctly. Many have rightly observed that this opens the door to many possible mistakes. So the natural option is to formalize the specification process. Many languages and tools for formal specification of software generally and protocols specifically have been developed. And these formal specs enable a degree of certainty about what the spec author meant, but they're a pain to write and to read, even for specialists. And so they've been considered really only worth it for the most safety critical applications. And then one can consider, well, if we have this formal specification, we can produce an automated implementation. A crisp enough formal specification should be easy to convert to code. So if you're going to go to the trouble to write a formal spec, you might as well automate the code generation. But formal specs have seen little adoption, and we're still writing protocol specifications in English. So our work, the first piece of which is appearing in SIGCOMM this year, takes a small step toward filling in the missing quadrant, taking RFCs, identifying ambiguities in the spec text, and then after the author fixes those, attempting to auto-generate code straight from English. Our approach is built upon a set of concepts and techniques in natural language processing known as combinatorial categorical grammar, which is a way to do what's known as semantic parsing, how to decompose a sentence into sensible units. And we're not natural language processing experts, we're networking people. So really what we wanted to do is take these techniques that have been developed in NLP and apply them to this context. We use this grammar-based approach rather than a more popular deep neural net-based approach because we wish to retain the structure of the text so that we can figure out whether multiple interpretations of a sentence are valid and how those should be fixed, if at all. So what kind of text are we talking about? Well, we want to be able to process excellent chunks of text like this. Or this. So we built a tool called Sage that attempts to identify ambiguity in RFC text, taking advantage of their structured nature and flag sentences that are ambiguous. Then for limited RFC features that we support, we take this disambiguated text and convert it directly into protocol code. Now, this is a very early stage tool. It's not ready for wider use. So really part of our motivation in presenting it to you all is to learn from the community and identify what are next steps of where we want to extend it to support. So in addition to parsing prose, RFCs have many types of structured text. Sage currently supports interpretation of packet headers and pseudocode, some aspects of state and session management, but does not support state machines or algorithm specifications. The latter are absolutely needed to support more advanced protocols. And so I come back to where I began, which is what makes protocols special. They're essential to everything we do today and have to work in contexts far outside their original intention. However, because as a community, there exist standardized practices for the development of RFCs, what I'd like to pose for discussion is how the process for standardizing RFCs might integrate semi-automated tools, like say a future version of Sage, to improve specifications and to produce baseline implementations. Thank you.
So thank you so much for that very interesting talk, Bharat. Can you hear us? Yeah, I already see people joining the queue. So, Stephen, would you like to unmute yourself and ask your question?
Hey, can you hear me? Yeah, so this is really interesting work. I guess my question is, how far do you think that natural language processing techniques can take us towards sort of fully automated code generation? You know, is there certain components of specifications that perhaps need, you know, more structured or more formal languages? You know, what's that gap like, I guess?
Mm-hmm. You know, to the extent that we have figured this out, and I have to say any answers I give at this point are going to be speculative because this is really sort of, we're taking baby steps towards this problem right now. I think that the first thing we want to target is the disambiguation piece. I feel like if we can really nail down the sources of ambiguity in the spec text, then the code generation piece, at least from our work on this so far, is the easier piece of it, because if you've disambiguated the spec, then you know what every sort of entity that you're talking about in a sentence or in a paragraph, what it means, what it's referring to. And once you've been able to do that, then a lot of it is specifications generally are going to be relatively hierarchical in structure. They're going to reference terms that have been defined somewhere. And so, the code generation piece, I hope is going to be the easier piece of that. Now, the disambiguation part gets tricky when, you're dealing with references that go way outside of the bounds of a specific spec. So this is one of the pieces where there's a vocabulary piece, which is relatively easy to figure out. In our paper, we talk about, we've just pulled in terminology from a networking textbook so that we knew that these were special terms in networking, right? And so we have sort of domain knowledge. And that's a kind of dictionary that can grow, but it's not going to continue growing forever. There are other pieces which are really about the sentence structure disambiguation. There it gets a little bit trickier. I'm not an NLP expert, so the answer I can give you here is going to be limited. But the way that we've sort of looked at that is, you could think of it initially as a grammar checker. That we have grammar checkers. Google Docs, for example, now does sort of auto grammar checking while you're writing. You could think of that as being an integrated feature. It's not going to give you 100% coverage on day one, but it's going to find, this sentence is ambiguous. Did you refer to the header, or are you referring to a message, or are you referring to, there's terms can be used in multiple ways, and you can have a tool that flags that. And then also the structure of the sentence itself, maybe the noun is missing. A noun is missing that leaves out the who it is that's doing something, sending a message, computing some value, so on. So that's sort of the first steps. Maybe, I'm happy to answer follow-up questions if that didn't clarify.
No, that was good. Thanks.
So thank you so much. I see Jana is in the queue. So Jana, would you like to unmute and ask a question?
I think I can be heard. I believe I can be, yes. Hi, Bharat. Thank you for this lovely talk. So this is super interesting because clearly you're familiar with the history of this work, and it's like when generally the space that you showed in that graph has been around for a good 25, 30 years. And to the point that you were making about IETF specs, one of the interesting things I find about, so I've gotten people write back to me saying this sentence is ambiguous when they try to translate it from English to a different language, because English fundamentally has some ambiguities which some other languages don't in some particular cases. And so when translating, they need to figure out whether I'm talking about the subject or what does this, the pronoun, what do things refer to, and doing that you encounter some basic pieces of ambiguity. So I think that can be, that I can understand. But the harder things I have trouble with in ambiguity, and we find this routinely in RFCs, is something that is the way that the text is written. There's a flow and there's context. So any sentence has context coming in before it. So depending on what the building blocks are, and this is what I'm missing in your work at the moment, is how are you building those semantic blocks? Are you using semantic blocks? You said you're not doing state machine generation. I get that. But just in terms of the language itself, are you doing some sort of, I don't know, I mean, I'm thinking about, the tools that are used for building summaries, for example, which do semantic block building and things like that. Are you trying to perhaps generate a summary of some pieces of this? How far do you think you can go with this? I would love for it to be able to detect ambiguity in text that is beyond just sentences and so on, to actually pull semantics out of it. That's a question. And in terms of a comment for you asking about where could this, or the potential for integrating something like this, I think this is super useful. Even at the lowest level, it could be used as part of things such as working group last call, IETF last call. The RFC editor does this work for us typically. Like there's a human who reads the text and says, hey, this sentence seems ambiguous. Can you please replace it? And they'll offer suggestions. So automation of any and all of those things would be super useful. And I think that the value of automation is in not waiting until later to bring those tools in. You just make it part of a CI for every PR that goes into the draft. When any new language that is introduced goes through this machinery, and then it figures out if there's any ambiguity introduced by it. So there are several places where this can be introduced, and I'd love to see that happen. So yeah, that's all I've got.
Yeah, thanks for all that. So to start at the beginning about the sort of the reference in a sentence. So this is co-reference resolution, something that's, a major studied area in NLP. We're using some co-reference resolution tools right now. We don't mention too much in the current paper, but sort of we're working on that right now. And, it's a problem that I guess can't be solved perfectly just because the nature of English text is, sometimes references can't be perfectly resolved. But the good news is that we can then flag potentially unresolved references, and then, that would be part of this automated tool. So that's sort of like the first stage. Then the question you had about, do we build up this sort of context of understanding? We don't do that right now. And so right now we've been mostly targeting simple protocols. And the one thing that's kind of amazing is that, for relatively simple protocols, often you can get away with not having too much context. As long as all the terms that are in each sentence you've already resolved those, you don't necessarily need a lot of history of, concepts that have been built up over several paragraphs to then understand it, as long as all those terms have been defined. Now, once we get to more complex, for example, algorithm descriptions and more complex protocols, we're going to have to resolve that. It's currently, we haven't figured that piece out. I guess maybe the way that I sometimes think about this is that this will especially be helpful for the long tail of RFCs or IETF drafts out there, which aren't getting as much scrutiny, don't have big working groups with a lot of intense work going on. But, there's all these smaller protocols that are out there, and someday some of them may become big protocols, protocols that people are depending upon, that we can never really anticipate that. And so it's good to be able to make sure that all of those get, some level of scrutiny, say through these semi-automated tools.
Thank you for that response. I'll make a quick comment before I walk away. Do not disregard the important protocols that are getting a lot of scrutiny, because those ones actually are the ones that need this kind of help more than anything else. What often happens is that you get scrutiny on the ideas, you get scrutiny on various things, you get scrutiny through people doing implementation, but not necessarily on how well the text is written. And that's, I would say that that's still a huge gap in my mind about there's a huge gap between intent of the working group and the text that shows up in the document. That tends to be, and that you rely on just individuals to fill that gap. It would be good to not be able. It would be good to be able to rely on automated tools to help enforce that intent matches what the text says. Thank you again for this work.
Sounds good.
So thanks so much, Jana. And I see Colin in the queue. Colin, would you like to read and ask your question, please? And I'm just going to close the queue after Colin, but please do remember that we have a few more minutes at the end of the session. So do join the queue if you have more questions for Bharat. Thanks.
Yeah, hi, thanks Anrw, thanks Bharat for the talk. I think this is fascinating work. I'd like to sort of echo some of the comments that Jana made. I think we're starting to see a bunch of different tools that people are applying to RFCs and to drafts. I mean, there's your work. We've seen people doing security analysis of some of the protocols. I've seen people analyzing state machines. We've done some work modeling protocol data formats. I think one of the challenges is that sort of analysis tends to happen when the RFC is published. And if we can find ways of building these tools early so they can be run routinely on the drafts, I think that would be a really nice way of improving the quality of the specifications before they're published. So I would really encourage you to keep working with the community here to try and integrate this into the draft publication tools and so on. I can introduce you to the tools team and so on if need be. And if we can help out with this sort of work in the IETF, then please do come and talk to me. Thanks.
Yeah, thanks. Exactly. We would like to integrate it with the sort of the draft stage rather than it being only, once it's final and published. The good thing is that even at the draft stage, it's just English text. So from the perspective of our tool, it doesn't know any different between the two. It will find ambiguities or not in either form.
So thank you so much again, Bharat, and thank you for the people asking questions. Do join us again at the end of the session. But for now, I'm just going to ask Meet Echo to queue up the next video for the next talk, which is from Ali, and he's just gonna give us a call for action for more collaboration. So thanks.
Hi everyone, my name is Ali. I'm a computer science professor and I have been working on streaming media since my PhD years. The topic for today is the very recent developments in the streaming space, in particular the common media client and media server data specs coming out of the Consumer Technology Association. These are the two specs that might have a fundamental impact on media distribution. I will give a brief overview of where we are today, how we got here, and where we go next. Without a doubt, streaming media is a big part of our lives. With more efficient media codecs, faster internet access, streaming any content we want is quite easy today. HTTP played an important role in this too. Back in the day, it all started with progressive download, which allowed us to play the media before having to download the entire media file. With sufficient bandwidth, this was a much better experience over the download and play approach. Following that, with some indexing tricks and the use of byte range requests, seeking in the media timeline was made possible, and servers also got a bit smarter. Yet the most important leap came out about 15 years ago with chunked streaming, which enabled live streaming over HTTP and splicing arbitrary content for things like ad insertion. The natural extension to chunk streaming was to generate multiple versions of the content and offer rate switching capability, in other words, adaptation capability to streaming clients. Today, all major streaming platforms use a flavor of this approach. In a nutshell, we have a source, which is live or on demand, that provides the mezzanine content, which is supposedly the best and most crisp quality that we can offer. The mezzanine stream is fed to an encoder or a transcoder that generates a number of representations according to a pre-selected bitrate ladder, which is a combination of resolution and bitrate pairs. These representations are then packaged into media segments and optionally encrypted, which are then published to the origin server. Through the help of the CDN caches, media segments can be efficiently accessed by the countless streaming clients. Why do we use HTTP? Well, it has all these nice features, works on almost any device, and goes through all the nasty middle boxes without a problem. The CDNs have a huge replication capacity and offer cheap and low latency access to everybody. HTTP is an object request response protocol, but with small media pieces, it can mimic streaming very nicely. And the ultimate goal is to make the viewers happy, at which HTTP adaptive streaming does a pretty good job most of the time. But adaptive streaming is not perfect either, so bad things do happen from time to time. Here's an example showing streaming client behavior. I have been showing this plot for more than 10 years now, so you might have seen this before. There are 10 clients streaming from the same server over a 10 megabit per second link. Ideally, all the clients should consistently stream from the same representation. In this case, it is the 866 kilobit per second representation. This way, the network capacity will also be used as much as possible. However, this is not the case, as you can see from the frequent upshifts and downshifts for each client. In a scenario like this, which is very common, we get either unfairness among the clients, instability for each client, or underutilization in the network. HTTP streaming traffic, which is in and off traffic and uses a set of discrete bit rates, cannot converge to the ideal point. If you are interested in knowing more about this, we studied this problem in detail in our NOSTA 2012 paper, which you can refer to for more details. Since these problems have been identified about 10 years ago, we and many other groups worked on finding a solution. Several solutions with different pros and cons have floated around. Now, when it came to the solution types, there were primarily three camps. The first camp was arguing that the service must always stay in control and the network must support appropriate quality of service. Otherwise, streaming video could never be on par with the traditional cable or broadcast TV. So their solution was to make everything more controlled with smarter and more expensive infrastructure. However, it soon became quite clear that the market has already moved on from more control on everything. The second camp was on the other extreme, argued not doing anything that will put more control on the infrastructure, but simply spending the money to improve the access capacity. In other words, the money should be spent to put more fiber under the ground and improve cellular coverage. As nice as this sounds, one thing we know for sure is that the demand for bandwidth is always more than the supply. The last camp was more pragmatic. How could we best use whatever the bandwidth or server capacity we have to meet the demand? So the last camp brought up the idea of some sort of a control plane that might enable information sharing between the servers and clients. This was certainly an interesting idea, but bringing together the developers of all the client implementations with the content or network providers wouldn't be as easy. But we were determined. In 2013, we stirred up enough interest to have a joint IETF MPEG workshop on this subject. Different proposals were brought to the table, and the discussions led to the development of the server and network assisted dash standard in MPEG. This SAND standard actually covered a lot of ground and established the control plane framework we always wanted. Despite all the academic research behind it, due to various reasons, this wasn't really picked up by the industry until a number of companies wanted to do something about it in CTA a few years later. That CTA effort first focused on the metadata information sharing from the clients toward the servers, and the spec was published last year as CTA 5004, and that's called Common Media Client Data. With this completed, the CTA started working on the sister spec a few months ago, which is for information sharing toward the clients, and it's called Common Media Server Data, and it's expected to be published later this year or early next year. So what has really changed the mind of the CDN providers? They didn't get on the SAND bandwagon a few years ago, but now they want to have something similar. Here is the deal. Whose fault is it when a user's video keeps freezing or is low quality? One can blame the device or the app or the internet connection speed or the CDN or the content provider. It's a vicious cycle that mostly ends up without a satisfactory answer, which makes us, the users, quite upset. Fault isolation is very important for keeping the paying customers, and it requires analytics data from various points along the delivery pipeline. There are many proprietary end-to-end analytics solutions today, but surprisingly, the CDNs are quite blind to all of this. CDNs see the requests and send the responses, but they don't have the glue to connect all the pieces together to get the full picture and identify how well things are working or not. The solution is quite straightforward, though. If with each request the client sends some identifiers and status information, the CDNs suddenly gain visibility into the media analytics. See this new paper from friends of mine to explore how powerful CMCD reporting could be. Here's a list of things a client can send information about. Even with a unique session ID sent with each request, the CDNs can now group the requests per playback session. which is already a big improvement over today's CDN's capabilities. Sending a deadline might allow for getting the response with a high priority, reducing the risk for video stalling. For example, CR announced a paper this year on the subject. Another use case is hints about the next request. The CDN may reduce the fetch time for the clients by using that information. On the other hand, the CMSD work is only a few months old, and there are already a number of use cases described by the working group. As you can see from the list, there are many ways the CMSD can help with, or many problems that the CMSD can avoid, which would otherwise be very difficult to resolve. The work is still ongoing. If you're interested, please consider participating in the effort. Developing or writing a spec is usually the easiest part. We hit the SAND standard, but it was not widely adopted. To get better adoption with the CMCD and CMSD, all of us working in this industry need to work together. We all agree that information exchange is useful when the information is relevant and actionable. The information also needs to be fresh. There are already a number of CDNs and clients supporting CMCD. So, for example, grab the latest HTS code, start experimenting yourself, and come up with how CMCD or CMSD can help in your environment. Both have extension mechanisms, so extending the functionality is pretty straightforward. And most importantly, join the effort and contribute. Review the use cases, propose new ones, and so on. With this, I provide a slide here with some useful links for your reference. And thanks for listening. And I hope those of you who are interested in streaming stuff and other multimedia systems topics can attend ACM Multimedia Systems Conference in person or virtually at the end of September. Thank you.
So thank you so much, Ali. Can you join us by turning on your mic and your camera? So thank you for that plug as well at the end for events list. So please do join the queue if you have questions for Ali. So the queue is open now. I don't see anybody right now in the queue, so maybe I'll just start it right off. So my first question, as obviously when you see this type of call for actions, is, okay, how much adoption have you already experienced right now, and which are the immediate benefits that you already observe? Just to, maybe trigger people to join the effort.
Well, certainly we have some folks today in the workshop who are representing some of the biggest and largest CDN companies. So I hope they will also join this conversation. But definitely there's some interest, because this time, unlike the MPEG standard we did like 5 years ago, this time the request came from the CDN providers. So that already shows their interest because they are really struggling with other analytic solutions, and they need something in place. Otherwise, they are just running blind, and they need to do this. Now, if only the CDS implement this, obviously that's not going to be sufficient. We need client support as well. And yes, there are some client implementations out there who already committed. But the big players like iOS platform, HLS players, AV library, I mean, they are not doing it yet. Maybe in the future they will, but not at the moment. But this can only be a great success if everybody who is involved on either the server side or the client sides, starts the implementation. And the biggest benefit, the second part of your question, is, as I mentioned in the talk, is even with some sort of unique identifier per playback session, the CDS will at least be able to understand, okay, this client is in this session and asking for all these files, all these segments and things like that. So they will be able to put up things together, at least per session. Otherwise, it's just, they are producing all these individual request logs, but they have no idea what they are for. So even with that simple request ID, I think there's a lot of benefit in there.
That's great to hear, and I mean, I do support that fully. And since the queue seems to still be empty right now, I'm just going to continue, and I'm just going to bother you with a few more questions. I liked very much your slide number 7 in the talk you gave before, just showing that different players just point the finger at the other, and it's very hard essentially to do root cause analysis for anomalies that might occur in this environment. And I'm just wondering, are you in touch with people who are looking at different deep learning, machine learning analytics for this type of anomaly detection approaches, or proposing ways for different players to share data in a privacy preserving way?
Well, when it comes to diagnosing your problems for your video services, it's not really very privacy. It's like there are a lot of privacy issues there, obviously, because whoever is looking into your problem will likely know what you were watching or what you were trying to watch, right? So I'm not really interested in that part. But when it comes to identifying where the problem is or what is causing the problem, obviously there are some companies out there who are doing all these probing type of things. They collect data from different parts of the delivery pipeline. They have some components in the client, they have some components in the CDN, they have some components in the head-end side, the packager, the encoder, whatever. The more probes they can put, obviously, the more visibility they will get. And collecting the data is one thing, then processing the data is another thing, and then reading the data and understanding the root cause is totally something different. And then all these different companies have different, success rates for that. But most of the time, unless really a CDN, goes down, like it happened a few days ago with one of the larger CDNs. But things do happen from time to time, or unless something happens with your ISP connection and so on. Most of the problem most of the problems are within your home network, or some software issues in your client side. So even if you have some components to understand what's happening in the client, then that will give you a lot of visibility. Okay, we made this change, and then here is the new problems started happening here and there, right? So most of these services often do A/B testing. So whenever they are testing with a new feature, they usually only enable it for a subset of users and see whether everything is working or not. So yeah, there are a lot of ways to diagnose these things, but just because you diagnose it doesn't mean that it's going to get resolved. That's another thing. And it's this finger pointing someone else or blaming someone else is usually what the companies do. So it's not that easy to get away from it. But with this, more data, at least you will have some proof, right?
So I see 2 people now joining the queue. So I'll ask David to maybe unmute and ask your question, please. So thanks for that, Ali, by the way.
Hi, did you unmute me?
Well, good to hear from you, David.
So I'm curious what the reaction of the folks supplying very large quantities of this video that believe they control essentially the entire delivery chain other than the ISP link. So for example, Google and YouTube, they control effectively everything up until the last top of the path to the user. Netflix today, in most cases, also does that. Do they see value in this kind of an approach, or only for people who, for example, the origins and the content owners are contracted with separate CDNs for delivery?
Well, okay, I'm getting some echoes. Maybe you might want to wait. So the larger set of benefits are for those people who, in the second bucket. For example, today we have Olympics, right? So the broadcast is coming from Tokyo, Japan, and then it's going to a bunch of service providers, video providers out there through multiple CDNs, everywhere in every country. Millions of are watching the content live. So in those cases, that's really the where the benefit is, because if something doesn't work, then now where things are falling apart. So for companies like YouTube or Netflix, essentially the problems are more limited in terms of where they can happen. Especially for Netflix, I mean, it's all on demand, so the content is already encoded, packaged, and it has been tested. So if something goes wrong, it's probably going to be in your home network, or maybe the ISP is the bottleneck at that time. So it's going to be relatively easy to figure that out. But for larger events, especially for live events, and when they're crossing across the different networks and different domains, then that's where the most of the benefits will be. And more direct answer to your question is, at the moment, I haven't seen anybody involved from those companies in this work.
So thank you so much.
Appreciate it.
I'm just going to open the queue for both speakers, and I'm just going to invite Bharat as well to join us. And so basically we're opening for the panel. I see Jana now in the queue, so please, Jana, just go ahead and ask your question. Thank you.
Thanks, Anrw, and thanks, Ali, for that talk. I want to push back gently on something that you said earlier about privacy not being important here. I think it is, and I think it's achievable. I don't think it's very far away. Just because I can see as a server, I can see the manifest, and I can see the videos you're fetching, doesn't mean that you have no privacy, right? All I need from a server's point of view is to be able to tie together the different videos that you're watching to be able to pull together a full picture of the video session that you've had. So if one of the problems I have as looking at logs at a CDN, I work at Fastly, is basically being able to pull together the different chunks that you requested as a client. So just the one single piece that you have in the CMCD spec of the session ID, basically, that alone gives me like 90% of the value that I'm looking for. So if I'm able to tie together just that single video session, that helps me tremendously because it shows me the bit rates that you've used. I mean, of course, the bitrate being explicit would also be useful, because otherwise you have to infer them from the object names to figure out what the bitrate might be, and so on. But those two pieces of information are hugely useful, and I think they can be done as you I imagine that the spec does that in a privacy preserving way, meaning that the session ID doesn't actually include the client's IP address in there or the timestamp directly. The timestamp is fine, but the client's IP address would be particularly problematic.
Well, the spec,
as long as that is done,
is not really involved in that much. I mean, obviously we hope and assume that the CDN provider will do whatever they can to preserve the privacy, right? Otherwise, all this information flowing back to the CDN servers will obviously, reveal some information. But how the CDN provider is going to use that information, that's really, I think it's a separate topic. It's
no, I appreciate that. I'm basically, let me be more specific. I think that the construction of the GUID, of the session ID, should be done in such a way that it doesn't reveal client personal information. That's if as long as things like that are taken care of, I think that the rest of it is still very useful and stuff that we can and want to be able to use. So thank you for this. I'm curious to understand the state of this work. As in, Anrw asked about the deployment. I want to understand the state of the spec itself. Like, where does it stand right now, and what's where does it end? Just because I don't know this particular space of
right.
spec work.
You must have seen the Fastly logo on my one of the last slides. Fastly is one of the CDN providers who's trialing this, and they already have some CMCD reporting. So they, some of your servers, at least, there's a trial going on. You can collect CMCD data coming from the clients, and then there's a dashboard where people can see what's happening and things like that. Akamai is the other partner at the moment, and we hope other CDNs will join the club. And as I mentioned earlier, this is not just the CDN support. The clients also need to send the information to the CDN, right? So DashGS and a couple of other open source players are currently also have some initial support for that. And with the other side of the spec, CMSD, the common media server data, I think it will be a lot more important for the CDNs, because now you will be sending some information back to the client. And at the moment, since we are just, working on the spec now, there is really no deployment or any trials, as to my knowledge. But I hope to see some action in that space later in the fall or late this year. So hopefully with CMCD and CMSD, and anybody can extend them as they like. There will be a lot of action in this space in the next year or so.
And where does one look for updates in this space?
Where does one follow what?
Where does one follow the spec? How do I follow the spec?
Well, it is under CTA, but there are 2 links in my at the end, in the last slide where you can find the GitHub links, and you can post the issues, and you can find the spec there. So it's a pretty open process at the moment. Thank you.
Thank you so much.
Sure.
So here's a really quick one. Is the session ID local to the client? Because if it isn't, doesn't that open you up to all kinds of interesting spoofing attacks, like piggybacking on other people's sessions and collusion among clients to make it look like they're all cooperating when they're not?
Well, the spec doesn't really say much about how you're going to generate the session ID, but it's not local to the client itself. So it's supposedly something unique, so that so that 2 clients or 3 clients within the same home or within the same neighborhood or city, whatever, they will not be able to come up with the same ID.
Just a quick suggestion that you do a security analysis of the scope of session IDs and how they can be abused.
Yeah. That's important, certainly. And you don't want to send wrong or bad intended information back to the CDN, because with your information, the CDN might take a different action. And obviously, the CDNs must be careful about what they process once this information comes from the clients. So that's one very big issue with this whole thing.
So thanks so much. I don't see anybody in the queue right now, so I'm just gonna take. Oh, I do see Jana. Jana, please go ahead. I'll keep my question for a bit later.
Oh, no, sorry. I didn't mean to take away from your question, Anrw. If you had a question, go ahead. You were in line ahead of me. And we have the chair's mic, so.
Right. I mean, I was just trying to bring it back to Bara, because we have been discussing about this open, this open space where we can contribute to the specification for Ali's case. But I'm just wondering, coming back to Sage, are you accepting at any point, or are you considering at any point accepting sort of contributions from the community, especially this community, in terms of maybe opening the tool and having people help with that? I'm sure you have tried it in a few RFCs, and I don't know if you want to tell us how that went as well. Yeah.
Yeah, absolutely. We would like to. We'd like to engage with folks in the community. We're kind of at this point where we've been working through the back catalog of relatively simple RFCs to start with. So, mostly to figure out, what are the essential features that we can actually disambiguate on and auto-generate code. But we would like to. I think one of the key things may be that, some of, I think in Colin's question, there was a mention of some of the existing tools that the community is starting to use, or folks that are working on, state machine analysis and maybe some of the other things. To the extent that we can integrate those kinds of things, where, say, there's a state machine analysis tool, but it needs to have a state machine, and the state machine is maybe right now specified in text. So, there's some things that are structured text that are in RFCs. Moving from that to something that is like an intermediate representation that then goes into a formal analysis. That's something that we'd like to be able to plug in with existing tools. One other thing is that the fact that we can use Markdown potentially, or even better than Markdown, something that's like structured formatting will be extremely useful. I don't know to the extent that that is being adopted widely across the community, but there's the more that we can structure the text itself while still keeping it easy to read and not sort of overly formalized, will make it easier for both human interpretation but also for machine interpretation.
Thank you so much, and I'm just gonna hand it over back to Jana. And sorry for mixing the two lines of conversation. Yeah.
Not at all. I actually had a question for Bharat too, and I'm trying to bring it back into my head now. I was going to ask about. That's right. So you said that you've been looking at some simple protocols. Can you give examples of which ones you've looked at and what your experience has been?
So in the SICOM paper, we cover the ICMP, the full protocol. So ICMP obviously being the simplest place to start, right? And so the reason we started there is we can go all the way from spec to disambiguation, fixing the sentences, to implementation that works with, ping and trace route, and, it interoperates. So, that was our first test case. Then what we did is we went through other RFCs across the years and picked bits and pieces from them that weren't sort of in the original ICMP RFC in terms of style of text or structure of text. So we have some text from NTP, some from IGMP, some from BFD. So those are the other ones. And then right now we're actively looking at some state machine, trying to pick which among the various protocols that have state machines do we want to try and analyze. And so we started looking at some. And so suggestions for those is like, that's one place to start. If there's one of the ways that we particularly improve the tool, but then it can be useful later, is protocols where it's known, probably through oral history almost in the community, that there was a spec that was really bad that was then improved over time. And to the extent that we have that history, we can then say, feed the original bad version in, and then we can see whether our tool can identify the things that human editors identified later on. And so it's not quite a training process in the way that like a neural net training would be, but sort of we can find whether our tool is even missing those things or not. So that would be the first place we could engage.
That is actually an interesting one. So one point where you could insert that tool might be before, well, there's a few points. It may not be in multiple RFCs, but in an RFC's life, you can catch it before it hits the RFC editor's queue.
Mm-hmm.
Because that's one place where a lot of English fixing happens. Is that the RFC editor will basically take a look and do a bunch of copy editing, and some ambiguity gets removed. That's usually, that's one place. But also around last call, again, the RFC is fairly mature by that point in time, but it goes through a community-wide review, and people will come and say, hey, people walk in with a fresh pair of eyes, and they'll look at the whole spec with a fresh pair of eyes, rather than the people who've been walking with the spec for 2 or 3 years. And so they all understand the context and don't necessarily refer to the text to know what needs to be built. So you'll find that the RFC before last call and after last call can actually be quite different. So those are at least 2 points in the process that I can point you to. If you take an RFC that's going into last call, or an RFC that's going into the RFC editor's process, and then put it through your tool and see what comes out on the other side. That might be something to consider.
That'd be great.
But yeah,
So much.
Yep, that's all. Thank you.
So thank you so much for this wonderful conversation. We're just 1 minute to the end of our session today and the end of the workshop. I think we had Colin in the queue, and that was fortunate because I would like to also invite both him and Nick to join me for saying asking the question, Colin, please, and then just saying goodbye and wrapping the workshop for this year.
Yeah, so I think we're short of time, so I will skip my question. But again, thank you, thank you to Baref and Ali for the excellent talks. Thank you again to Anrw, to Nick, to all the other authors, to all the presenters, the program committee members. I think this has been a really interesting program. That there's been some really excellent talks, some really excellent papers, and we've seen some really interesting questions here. And I have certainly learned a lot over the last 3 days of the workshop, and I hope other people have too. Thank you also to the sponsors, to Comcast, to Akamai for supporting the fee waivers, for supporting the workshop, and in going forward for supporting the IETF to help improve access and the diversity grants. Yeah, and if people have feedback about the workshop, if people have ideas for what to do in future, please talk to us. Please talk to me, to Anrw, to Nick. I'd like to just finish up by encouraging all the authors to join with the rest of the IETF, the IETF sessions this week. I think one of the benefits of the ANRW is co-locating with the IETF meeting, and obviously this is a bit harder doing this online rather than doing it in person, but please do try and make the most of the opportunity. And yeah, we'll do this again, and hopefully we'll do this in person in future. So yeah, that's all I have. Thank you again to the organizers. I think it's been excellent.
Thank you so much, Colin, and thank you so much to the speakers, the participants. Oh, I'm getting some feedback, sorry. And it's been great working with you, and yeah, it's been great taking care of the workshop this year. Looking forward to seeing you in Gather if you're roaming around there. So that's it for today. Thank you again so much. And thanks Nick, thanks Colin. It's been great.
Thanks again. Thanks for all the hard work.
Thank you.
Bye. See you soon.